Hello and welcome to this quick introduction to Opera simulation software from Dassault Systems. This presentation looks at the use of Opera for analysis of superconducting devices. Opera has been in commercial development since 1984. In 2018, Opera joined Dassault Systems as part of the Simulia brand. Simulia comprises simulation software for different physics at different scales. Finite element simulation is well established for modeling DC superconducting systems, and the methods are well understood. In MRI, for example, an accuracy of a few parts per million is required for the central field magnitude and homogeneity in order to obtain good quality images from the device in operation. Obviously, any virtual prototyping tool must be able to match this with solution accuracy for it to be of any value, and rarely is the fact that the coils are superconducting taken into account when undertaking field homogeneity calculations. As systems with AC fields gain popularity, including the properties of superconducting materials has become more important. We'll look at this comment in more detail later in the talk, but for now, let's take a look at some applications that use or have the potential to use superconducting material to great effect. We'll start with some of the well-established DC applications and move towards those that are emerging, including some that are essentially AC. The magnets used in high-energy experiments and particle accelerators, which are often one-off physics experiments like the Joint European Torus or ITER, and large particle accelerators like the Large Hadron Collider at CERN, demonstrate the most successful and varied use of superconducting technologies. A driving factor for this is that they require the enhanced magnetic electric properties in order to construct a functional system, and the development costs of using superconducting materials and the cryogenic systems required are not cost prohibitive. The use of finite element simulation of the design of these systems is essential, as the development cost of creating generations of physical prototypes is prohibitive. In this area, superconducting windings are used in magnets for bending, focusing, and confining particle beams, as well as for conducting experiments and detecting the results. The main simulation requirements are accurate calculation of the magnitude and gradients in the fields produced in both DC and ramping operation, and protecting the system against faults due to quenching. Simply put, a quench is the transition of the materials in the magnet from superconducting to resistive state during operation. If no care is taken to manage the transition in a controlled way, systems can be damaged or even destroyed. Managing against superconducting quench is also a common consideration in MRI magnets. In MRI systems, the superconducting coils typically fall into two categories: those designed to produce the homogeneous central field region, known as the main field coils, and those used to reduce stray fields which can damage nearby equipment or endanger patients in communal areas. Care must be taken when ramping the magnet to operational levels so as not to quench the niobium titanium coils with heat generated by rate-dependent losses in the coils themselves, or eddy currents produced by the changing fields in support structures. Here we have a demonstration model of an MRI magnet, which includes the coils, formers, spacers and coolant pipes being ramped to operational fields over a period of nearly 3 hours, showing the current as it's ramped and the resultant maximum temperature rise during the process. In this case, the ramping is slow enough for the whole coil to remain below the critical temperature of 9.2 Kelvin, above which the niobium titanium will become resistive, quenching to potentially disastrous effect. Further evaluation of this system during a quench can be made given the transient field as the current drops and the temperature distribution in the coil. This in turn can be used to evaluate the stress in the coils at any time, which can include contributions from pre-stress or winding tension, thermal expansion of the coils, Lorentz and other electromagnetic forces are acting on the coils. The use of superconducting materials in electrical machines is not a new idea. Concepts have been put forward since the late 70s, and test machines have been developed over the last 30 years with reasonable success. However, it's only really been in the last 10 or 15 years and the discovery of HTS wires coupled with the drive to reuse renewable energy that this field has really gained momentum. One example of a real device constructed using a DC superconducting field winding is the prototype developed under the European Union FP6 project named Hydrogeny. This is a 1.7 megawatt hydro generator that was developed in an industrial partnership. In this case, simulation was able to predict the performance of the device with high accuracy, including estimating efficiency to within 0.1%. The generator has demonstrated that it's possible to reduce the size and weight of a generator for this purpose by up to 70% with significant improvements to efficiencies. Whichever virtual prototyping technique is employed, a description of the device is required covering its geometry and materials used in its construction, the physics that govern its operation, and so on. The technique must also provide a means to solve the physics and characterize or review the results. And the most common virtual prototyping technique across any discipline is the finite element method. However, even using this method, it's still not practical to include a description of every filament in a superconducting wire, or even every turn of wire, in a system level model of a device due to its limitations in what can be processed in a realistic time frame. This statement can be highlighted by looking again at the bismuth wire used in the high field coil I showed earlier, which contains several hundred filaments of superconductor in a supporting matrix. Clearly, the number of elements we'd require to resolve even a short section of such a wire would be excessive, let alone many coils of many turns contained within a larger system. Instead, in system modeling, we typically use a bulk homogenized approximation for the coil as a whole, based on the relative fractions of the component materials in the coil. We can use expressions from theory or tabulated data taken from measurement. Here we look at the thermal properties, which are very anisotropic, so the bulk approximation needs to accurately represent the winding, not just as a single bulk value, but typically in both the direction of current flow and perpendicular directions. This means that some method of describing the current direction is required so that the anisotropic material properties can be aligned with this local orientation, rather than with a global system or some simple transformation of the global coordinate system. One important characteristic when considering a potential fault in the system is that of the critical current. This highly nonlinear property varies with both temperature and the flux density the winding is exposed to, and it defines the point at which the transition between normal and superconducting state occurs. Clearly, in a homogenized model, where the current flowing in the superconducting filaments is distributed equally in the volume fraction of the superconductor and matrix, the critical current density must also be diluted using this volume fraction to enable the bulk to transition correctly. If you're interested in validation of finite element methods for the simulation of an HTS material in an AC application, I'll mention this one test case. In this, we're operating in the mixed state where external oscillating magnetic fields are driving the induced current flow into operation above critical current density. The results of this analysis were verified against the theoretical predictions of Brandt and Inderbaum. A case study describing this work in detail is available through our website, operafea.com, so please see that for all the relevant details. This brings us back to the discussion regarding homogenization. In DC systems, one of the properties, that of diamagnetism or the Meissner effect, can be included in a system-level simulation as a bulk property, simply by setting the permeability of the superconductor to below unity. This approximation is valid assuming the conductor remains superconducting, though the fields the conductor is exposed to can no longer contribute to the transition. Another method of including the Meissner effect suitable for DC systems is one proposed at the Applied Superconductivity Conference in Houston in 2002, where the available screening current and the incident fields on the superconducting material are used to determine an equivalent magnetization for the bulk material, which determines the magnitude of the diamagnetism. Here the mixed state behavior is better approximated, as this method enables the inclusion of the hysteretic, irreversible behavior of the filament magnetization, which contributes to the fields. Again, this is only suitable for an effective DC system, as the contribution to the transition between normal and superconducting state of the screening currents isn't considered correctly. In AC systems, similar to the filament level simulation we've already reviewed, where the filament magnetization and hysteretic losses, along with the relationship of transport and screening currents and the transition from purely superconducting to a mixed state behavior, is important to obtain an accurate description of the fields produced, work is still ongoing in determining a method suitable for rapid prototyping of such systems. Approximations again include homogenization of the materials constituting the winding and lattice, however now with the inclusion of insulation boundaries between individual turns or highly anisotropic conductivities to restrict the path of current flow between turns in the coil. This implies it's still necessary to resolve the current flow in individual homogenized turns explicitly, as it's not uniform as in DC systems. One caveat to this is that recent advances in parallel processing are enabling more complex problems to be tackled. To this point, in this section, discussing the modelling of superconducting materials, we've looked at only the electromagnetic properties of the coils. However, in superconducting systems, often the thermal and structural properties are also of interest. One such situation, as described earlier, is that of superconducting quench. Here we're simulating the transition from superconducting to resistive states driven by the propagation and generation of heat in the device. In an AC system, it's much more difficult to detect and hence protect against due to the slower, smoother transition from purely superconducting through mixed to resistive states. Once a quench has begun, we have two design issues to deal with. Detect that the quench has started and protect the magnet from damage. Here's a typical protection circuit for a multi-coil DC superconducting magnet. As the superconducting material transitions from zero to finite resistance, the current will preferentially choose to flow through a small finite resistance rather than the resistive superconductor, which now has higher resistance. This reduces the ohmic losses in the conductor, protecting the magnet from overheating and allows the cryogenics time to cool the windings. However, the reduction of current flow in the windings will cause a rapid quench in the fields produced by that coil, potentially causing neighboring coils to quench due to rate-dependent losses or losses in other conducting structures that oppose the field changes. Here's a validation example of an experiment in which comparison is drawn between simulation and experiment for a quench process. The coil set consists of 4 superconducting coils and an aluminium former. During an initiated quench, all of the coils quench despite being electrically and relatively thermally isolated due to the rapid field changes and rate-dependent losses. We can also determine and visualize currents induced in the aluminium support structures, perhaps enabling us to make considered design changes to reduce these effects. This test case is available on operafea.com. Please check there for more details or contact us. Thank you for joining us for this quick overview. Please don't hesitate to contact us for more information on the subject or check the Opera or Dassault Systems websites for further details.